small.
Sorry.
Okay. The title of my talk is actually the title of
Ron,
a
sorry.
workshop.
Oh, sorry, could you please come closer here that we have
Sorry.
microphone on this side?
Okay. Why don't I come over on this side? You're blocking the screen. The title of the talk is also the title of a workshop that was just held at the Lorentz Center beginning of this month that I had the pleasure of chairing. So my talk is going to be two parts. The first part of my talk, I'm going to be talking just about sort of the results from Gaia, focusing on the results in Gaia, and much of the work that we've been doing also in Torino with respect to exploring the kinematics of the Milky Way and a little bit of work in progress. Then the second part of my talk is going to be putting those results, what Gaia has been telling us about the Milky Way, in context with other data types of data, so from the near infrared to the radio. So sharing some of the things that were shared at the workshop. So let's see if this will now work or not.
It doesn't work because there is the acceptance required.
Now, what did it do? Okay, there we go. Now it's working. Not sure. There we go. Okay, so as people know, Gaia gives us lots of information: positions, parallax, proper motions, and line of sight velocities. And from these, we can derive positions and velocities in so six-dimensional space, phase space, as we usually call it. We started looking at one of the interests that I've always had scientifically, and what I was always excited about using Gaia for was exploring the Milky Way. In fact, when I first went to Torino, it was to work with the Hipparcos data. And the first project that I worked on was looking for the kinematic signature of the galactic warp in the Hipparcos data. And we didn't find it, or rather we found a signature that was completely contrary to what we expected. It was sort of a mystery. It wasn't until Gaia, the second data release, that I, together with a student that we had there in Torino, Luis Napoleon, who's now a postdoc in Nice, where we were able to clearly see the signature of the galactic warp, and also understand why we weren't seeing it in Hipparcos, because the signature was expected to be large enough that Hipparcos would see it. And it was a combination of things, of systematic distance errors, of small rotation in the Hipparcos reference frame, and the fact that the warp signature itself, the magnitude of the signature, was smaller than expected. And it was later, trying to model what we were actually seeing in the Gaia data, that we found that what we were seeing was, in fact, a warp that was not static in space as the stars were going around the galaxy, but a warp that was had a shape that was precessing in the prograde in the same direction as rotation, making the vertical velocity smaller than you would have otherwise. And this is sort of, I'm not sure if I can make this go or not. Maybe not. Well, this is supposed to be a movie somehow. There we go. There we go. Just an animation sort of showing how fast that precession is with respect to, say, the sun going around the galactic center. In the vertical, the warp there, you can see a bit more clearly. You can see it's not a super strong warp, but it's definitely, looking at edge on, you would be able to note that the galaxy was flipped. With regards to spiral structure, Gaia has been revealing new things about this. And the first evidence of galactic structure in our galaxy began in 1953 with Morgan, when he mapped OB associations nearby. In there, he could see that there were essentially signature of three spiral arm segments. So the inner one toward the inner, these are, by the way, the old galactic coordinates. Galactic center is actually more in this direction. And so let me see if the pointer will work. How do I turn on the pointer? This maybe is it. There we go. So this would be Sagittarius. This would be what was called the Orion arm, and this is Perseus arm. Now, of course, what we would like to be able to do is make a portrait of our galaxy and know what the galaxy would look like if we were able to look at it from outside. This is an artist rendering that was recently made by someone who the same person who made the video that I showed earlier. So this is where we would like to be able to reconstruct what our galaxy looks like. But it's of course difficult because we're inside the galaxy. This is the whole challenge. We can't see the forest for the trees, literally. But using Gaia data, we started mapping out the young stars, the traditional tracers of spiral structure, being young stellar populations. And here you see the data from our upper main sequence sample, and using a technique that Eloisa developed, plotting the over-under density of the distribution with respect to the surroundings to pull out the contrast in the features. And here again, you see clearly three segments. This is the Sagittarius, maybe a bit of the Scutum arm that not clear if we're actually seeing that or not. The local arm with the sun just inside, and the Perseus arm. And now I'd like to just compare what Gaia is mapping here with respect to sort of spiral arm models that have been done in the past. This is showing now in black dots are large open clusters. You see that there's consistent, but there's of course more scattered in general. The arms that are traced here are from a popular spiral arm model called from Taylor and Cords, 95, I believe that's from. And you can see that while one might convince yourself that the Sagittarius arm looks okay, the Perseus arm, of course, is completely different than what was expected from this model. Looking at now, this is a different, these trace out a more recent spiral arm model based on masers by Reed 2019. These black crosses are in fact the positions of the masers. And again, like the open clusters, you see that along the arms, yeah, we have more masers. But of course we have here in this third and fourth quadrant almost no data from masers. It's not because I'll show later that that's not because of lack of masers, but it's simply that we don't have parallaxes yet to objects, to masers that are in those quadrants.
Sorry, Ron, just a curiosity. According to this map,
Yeah.
it looks like the sun is some kind within another density.
Yeah. This is just because in Gaia you don't see the bright stars.
Okay, so it's a selection.
It's a selection effect,
Okay,
yeah.
okay.
So you have a little bit of a hole there in the center. And we have tried to, in the recent paper that we had in DR3, we did actually try to fill that hole in a bit. It's probably about 1,000 stars. You can use other catalogs to put them in there. It's partly a selection effect, not just in Gaia, it's a part of the selection effect of how we built the sample as well. And then, okay, one last arm dimension is this one traced out in dashed lines. That is an arm that was traced in H1 by Levine. And you can see actually that the Perseus arm does actually follow that arm there. And going forward, so just sort of zooming out to sort of, again, this is the Taylor and Cords model and over tracing the Levine arm, the outer parts. And you can see, of course, that in a sense, in the Taylor and Cords model, there really isn't a local arm, isn't part of their model. But something that I think is worth pointing out is that this local arm is not so local. Yeah, it's we're tracing it out here at least over a length of 8 kiloparsecs. And certainly, especially in this direction, it extends even further, I think. So yeah, it's not a small feature. It's not a major arm in the sense that it's definitely weaker than both the Perseus arm, at least up to this point. Perseus really peters out quickly after this part here. It's very weak. That people have noted that for some time in the literature. Yeah, so let's go on and see what else we can discover here. Now, this is just going back again. Where are we now with respect to Morgan? And you can see what's interesting is that the data is very consistent. Our models of spiral structure has changed a lot over the years, but the data is very consistent. Yeah, Sheffield and Morgan. A different tracer that we might try to use is Cepheids. And I don't have a slide for it. The Cepheids trace out beautifully the galactic warp. There was a paper a couple of years ago by Skoron where you can really map out. And the nice thing about the Cepheids is that they really cover a larger area of the galactic disk. You don't have the inner parts of the disk, but that's a metallicity effect. And of course, they are sparse. They're not relatively rare objects, actually, but you can see them far away. And here, so this is the OB stars, and it's hard to say in this inner region whether the Cepheids are really consistent or not. Here, what we tried to do is apply a wavelet technique to try to do the same thing we were doing here with the overdensity, trying to pull out where the signal is. And you can see that maybe we're tracing out here this outer arm. And recently, during the workshop, when I wasn't busy organizing and directing things, I was trying to play around with a little bit of this data some more. See if we could pull out something with the Cepheids in terms of galactic spiral arms. So here's the Cepheid data again, now plotted as a function of galactic azimuth, where this is azimuth prime, 0 is in the direction of the anti-center. So on the right, you have the first and second quadrants, and on the left, you have the third and fourth quadrants. And I've plotted galactic centric radius as a function in logarithmic scale. And in this plot, if you have logarithmic spiral arms, they should show up as linear features. The right-hand side is just a mess, and that's mostly because of what I call shadow cones due to extinction that are causing gaps here. You can't really see much in the first and second quadrants, but you do see a couple of distinct linear features here. And now, if I take out the oldest one, so this is the dynamic, what I call the dynamically young Cepheids, you still see those linear features sort of showing up here. The ages of the Cepheids are problematic. They're quite uncertain, but my attempt to try to pull that out a little bit more. Now, if I actually sort of select those two regions there, and I ask myself, where in the XY space is that? So this is what the Cepheids look like in XY space. You might, and what I was pointing out as the outer arm was out here, or the extension of the Perseus arm, and you might see something out here, something a trace. In fact, that's where those two linear features show up with that. So this is sort of still work in progress. But I think some people have claimed you can map the spiral arms to the other side of the galaxy with the Cepheids. I don't believe that at all. But what's interesting about the Cepheids, though, is even though the first and second quadrants is a mess, and the Cepheids aren't very helpful in this part of the galaxy, they are helpful here. And as we'll see in my later slides, that's interesting because for the masers, it's exactly the opposite. We have lots of data in the first and second quadrant. We have almost no data in the third and fourth. So it's complementary, I think. So spiral structure on a kiloparsec scale is what Gaia is showing us. And it does not agree with the common models in the third and fourth quadrant for sure. The local arm is not so local. I would like to, instead of calling it the local arm, go back to its original designation, which is the Orion arm. I think it's large, it's long enough, it deserves a name. The reason why it was called the local arm was demoted to local arm Because when the first 4-arm models of the galaxy came out, based on H2 regions, the local arm didn't fit. Right? So people say, well, it's just a minor feature. It doesn't deserve any. And it's not one of the major arms. So I again agreed it's not one of the major arms, but it is definitely, I think, not just a local spur, as many used to claim. So other things with Gaia, kinematics. This is not work that we've been doing. I was involved a little bit in this work, but one of the many authors. This discovery came out of a DR2 paper, sort of a follow-up on a DR2 paper. Those of you involved in Gaia know that we have access to the data to do those papers that accompany the data release. We have I think a 4 to 6 month lead, depending on the data sets or which data we're looking at. And so for DR2, there was a paper on mapping the Milky Way, the kinematics, using the subsample of source that had line of sight velocities. And this wasn't part of this paper, but after we had to submit the paper at least 2 months before the data release. And this was sort of like a mystery. Teresa was looking at these UV plots and other things, and she was seeing this signal, and she at first thought it was a mistake. It was and she was but we decided to leave this out, of course, and she was continuing to try to follow up and but she convinced herself that, no, this was not a mistake, it's real. So soon after DR2, we published this result here. Very nice. You see that this is called the phase spiral, or a snail. And essentially showing that there's this correlation with the vertical velocities and where the stars are positioned in the above or below the plane of the galaxy. And that comes out quite here. This is just showing the densities. It's quite a subtle feature, but it really pulls out when you color code the stars as according to V5. So essentially that the vertical motions and the motions in the direction of rotation definitely have a correlation. And this was shown to be sort of this classic signature of phase mixing. So something disturbed the galactic disk in the past, and it's still kind of wobbling around and settling down from that disturbance. And we're still open question of exactly who's responsible for this disturbance. Maybe Sagittarius Stork, but this is still sort of a work in progress to understand exactly how long ago was the interaction that caused what we're seeing now. What's really exciting now, this was using just the sources close to the sun. But with DR3, we have even more data with radial velocities. Again, oops, I'm going back to pushing the wrong button here. So this is, again, the local volume of high quality data. And Jason Hunt realized that actually the local volume was probing other parts of the disk. And if you bin the data, use the angular momentum of the stars to bin the data according to guiding radius, essentially, you could look at the stars in this volume over different radii. So differentiate the stars that came from the inner parts of the galaxy with stars that came from the outer parts of the galaxy, and see again that signature is actually over quite a large extent of the disk. But you can do it not only in radius, you can even go also what's called a conjugate angle of the angular momentum to probe a certain small range in galactic azimuth. So we actually take this data and bin the stars according to where they came from, so to speak, where their guiding radius is. And it's over, this is over a range here, they can't see it, over a range of plus or minus 25 degrees in galactic azimuth. And in the horizontal direction, this is again guiding radius. So the inner parts of the galaxy and the outer parts of the galaxy toward the right. And see how that spiral changes a bit. And I don't have people, he's also now working with others simulating this kind of thing. And I had a really cool video that I didn't have the courage to put in my slide set because it was really a huge video. But anyway, so the goal now is try to model what we're seeing here. Something that you might notice is that in over most of the extent of the disk, This phase spiral is a one-armed snail type Archimedean spiral. But if you look in the inner galaxy, you actually see two arms. And that's the distinction. Jason explains that as the outer part, over most of this, you're seeing essentially a bending mode. In the inner parts, you're seeing a breathing mode. Anyway, interesting stuff. So lots of stuff that Gaia is showing us. So this is the DR2 paper that I was mentioning before. Now, this is mapping the velocities in the XY plane. The left-hand plot is the radial velocities, what I call radial velocities with respect to the Galactic Center. Okay, so, and d phi, so in the direction of rotation. Now, a couple of things to note is that, well, the first thing is obvious. The galaxy is not actually symmetric. Yeah, if the galaxy was actually symmetric, there would be no radial velocities. And you'll notice that these curves of how do you say isovelocity curves are not radial either. So these are not just simple radial waves. Yeah, you'll see that from following. It's more obvious here, but it's traced out along the zero. This black shows the zero. You also note something curious, that the zero passes near the sun. That's by construction. Because at the time when we made this map, we derived the galactic centric velocities, assuming the LSR was in circular motion. And that assumption means that you will, by assumption, the sun, at the position of the sun, you're at zero radial velocity. So, but let me turn around here just because I like to put the galactic center to the right. The reason I did flip it over, it's the same plot, just flipped over, because in the DR3 work, we did the same thing. Now, I mentioned that we're deriving positions and velocities to make these maps, right? If I just use Gaia data, what I get is heliocentric positions and heliocentric velocities. So what do I need to go to galactic centric velocities? What do I need to know to go from heliocentric velocities to galactic centric velocities?
Distance of the galactic center.
Huh?
The distance of the galactic center, for instance.
Maybe, yeah. What you need is the velocity of the sun in galactic centric coordinates. If you have the velocity of the sun in galactic centric coordinates, it's just a difference. Because the observed velocities is the difference between the sun's velocity and the other object's velocity in galactic coordinates. But you have to get the sun's velocity. Now, what traditionally has been done in the past is what we did with DR2. You assume that the sun's velocity is a component of a circular motion, the LSR. So you assume the LSR is in circular motion, and then you drive somehow using a local sample of stars the sun's motion with respect to the LSR. Okay. But if the galaxy is not actually symmetric, right? If the galaxy is not actually symmetric, do we have any reason to believe the LSR will be in circular motion? But the good news is we don't have to use this approach, right? Because thanks to not Gaia, but to near-infrared astrometry, using an instrument called gravity. So the gravity collaboration came out with this astounding result. In 2018, their paper was something like, we're proving that Einstein was right yet again, because we can see gravitation, the relativistic effects in the orbit of one star that's going around the galactic center. Hidden in that paper, in an appendix, in a table in the appendix, was R naught. To an astounding precision that had never been done before. Yeah, and they didn't even talk about it in the paper. It was hidden in the appendix. What also was hidden in that paper is the velocity of the sun toward the Sagittarius A star. Now this is a sim that's updated. They've come out with a few other papers. They now have a solution based on 4 stars, not 1 star. And now we have R naught to 8.277 kiloparsecs plus or minus 30 parsecs. That's like a 1% error. I mean, it's just absolutely amazing that we now know, this is one of the main, when I was in graduate school, you know, there's two main galactic constants, the distance to the galactic center and the velocity of the rotation at the sun's position, right? Well, we had it already.
Are the two estimates compatible with each other? Because it looks like
No.
before, so.
So the error, this error, which is supposed, by the way, this error, according to them, should include systematic errors. But this error may be a bit optimistic. Still, even if it's off by a factor of 2 or 3, still an astounding precision. So I think, yeah, we can say that we know where the sun is with respect to that. So, now what's also nice is that we have from radio astrometry, we have also the proper motion of Sagittarius A star. It's the apparent motion of the galactic center on the sky. And that's nothing more than the reflex motion. It's really the sun moving with respect to the galactic center. And we're seeing that as an apparent motion on the sky of the galactic center. And also, again, thanks to radio astrometry, really an amazing precision. But now if we have the motion of the Sagittarius dwarf, and we know its distance, right? We can actually then derive the sun's motion in galactic centric coordinates. Right? And now I can derive the velocities of stars without assuming anything about the LSR. So I pointed this out in a research note a couple of years ago when the first results came out. It still hasn't quite caught on. People still have this traditional, you'll still see people usually do the LSR decomposition. In the DR3 paper, when we mapped the velocities, we took this as the galactic center, the velocity of the sun with respect to the galactic center.
So you don't need anymore to go through the correction to the LSR because you go straight in the galactic.
That's right. And the reason why, another reason why, if you look at the uncertainties, even if you want to be generous and multiply by 2 or 3 times, this precision that we're getting here is better than, say, especially when you have take into account that the solar motion with respect to the LSR has its uncertainty, and then the motion of the SR has its uncertainty, right? So this is definitely better. So now we can map DR3. We took giants and we mapped their velocities. I have to say that when we first saw this map, there was like a collective jaw drop. The project, those of you in Gaia, these science papers that come out with data releases, a few years before the data release, there's like an open call in DPAC saying, okay, let's hear some ideas of the kind of papers that we can come out with. Of course, you know how that process goes, right? And so you have to sort of make a proposal for a paper, and then the executive council of DPAC chooses amongst the proposals, chooses a set. So when I made this proposal, the proposal was to look for spiral arms, but we got slapped in the face by the bar. Really, I mean, we didn't. First of all, I didn't expect us to go all the way to the galactic center with the giants, because remember, this is a subset with line of sight velocities. Yeah, and so I expected to go out maybe 5 kiloparsecs from the sun. I didn't. This was just a total surprise to us. The other surprise is that, of course, the quadrupole signature here is just because I could have added another slide. Because the stars are essentially going out on one side of the bar and coming back in. Their orbits are elliptical along the bar. So this is why you have this signature, quadrupole signature in the velocities. This ends about. It's expected that this kind of signature ends around co-rotation. So we were able to get a good estimate of co-rotation. The other thing is that you see other systematic motions, you know, positive and negative on this side. And this, again, this is still mostly dominated by the bar. There's no clear signature of the spiral arms, at least in the radial motions. The radial motions are completely dominated by the bar all the way out to 10 kiloparsecs, which is sort of the expected distance to the outer limb that resonance of the bar. Yeah, so this on the right here is the velocities along in the direction of rotation. See the elongation of the bar. So going back to the Cepheids, so this was also kind of exciting to look at this population because we had even better distances. We have a lot fewer objects. Before we had, I think this previous map was based on, I think like 5 million. So this was something like I think it was about 5 million giants. So in the Cepheids, we have many fewer sources. Those with line of sight velocities is about 2,000. About 2/3 of the known Cepheids have good measurements on the line of sight velocities. But because their distances are really good, we can be pretty confident that we are able to get good velocities for those, because you need the distances to get the velocities. And when we plotted those, sort of something that popped out is this apparent gap here. And now mapping with respect to radius and angular momentum, you see that that gap is actually at a constant value of angular momentum. So it's sort of a classic resonance feature. And so I asked, well, what resonance could possibly be out there? It just so happens that that radius is at the 1-to-1 radius resonance with the bar. But I don't necessarily, I'm not saying that that's what it is. It's at the right position, but kinematically, if you look at the theory, you don't expect any signature of the bar at 1-to-1 resonance. So it might be something else. It might be a resonance with spiral arms or signature from an interaction. Yeah, it was even, thought someone's proposed that it might be just a selection effect of the spiral arms can introduce these gaps if you sample over a narrow range of azimuth. Actually, we're sampling not over a narrow range of azimuth, so I don't think that's the case. But, so something definitely going on to be understood. Now, the rest of my time, I'm not sure how much time I have left. I'm going to try to go through this. I'm going to just go quickly through some other things, not Gaia. Well, actually, some things are related to Gaia. So Gaia is not just about stars. We can map extinctions with Gaia because in the last data release, we had astrophysical parameters for not all the stars, but for a large number of stars, and that includes extinction. So this is a 2-dimensional map that I made with other colleagues for the third data release. This is this map you can get from the the Gaia archive. And this is a map of total galactic extinction. So essentially, we chose selected giants that are outside the galactic plane and looked at their extinction values. But thanks to Gaia, because these astrophysical parameters are attached to stars for which we know parallaxes, this 2-dimensional map can be actually turned into 3-dimensional extinction maps, which is essentially, there's a whole industry in the literature of people generating these 3-dimensional maps of dust in our galaxy within the 2 or 3 kiloparsecs of the sun. And the most common one right now being used is by Lorentz, who gave a very nice presentation at the workshop. Not only about her work, she actually gave a review of all the different kinds of methods and maps that are being produced. So this is definitely going to have a bright future because the astrophysical parameters are going to get better and better with each data release, both because of better data, but also better methods. But this is a challenging problem. It's an inversion problem, essentially, to turn these extinction measures into densities. Another interesting talk was at the workshop was given by Michael Kuhn, who looks at young stellar objects. So these are usually identified in the near infrared, matched with Gaia. We get their distances, and you see that there's very good correlations with the dust map. So very nice work there. Again, but limited within, say, 2 or 3 kiloparsecs of the sun. Another interesting talk was given about the DIBs. These are diffuse interstellar bands. I'm not sure how many people here know what diffuse interstellar bands. They've been known since the 1920s when they were first discovered. And since they're just, there's discovery, there's like hundreds of these lines that have been identified in the past years. And only 4 of those lines have we identified the molecule. The other, all the other lines were yet to be, identified the molecules that is actually responsible for these lines. So it's sort of an interesting mystery. This is the molecule that was actually identified, but one of the buckyball C60, I think it is. So complex molecules, yeah. The interesting thing with that Gaia in DR3 is that with the high resolution instrument that was measuring the line of sight velocities for Gaia, one of these lines shows up. And for some of the stars, you can actually find the profile. And so we can actually map, essentially this is mapping the equivalent width. So it shows how strong how much column density you have to given stars. This is a 2-dimensional map, but sort of like extinction, right? All of these measures are attached to stars for which we know their distance. You can see how the equivalent width increases along different lines of sight. And so this, eventually, the next step is going to be going from this 2D map to 3D map, and people are working on that. And the other really exciting thing about DIBS, I think, is that it gives you kinematics. Because you know what the rest wavelength of this feature is, and you can see how it changes along the different lines of sight. So here, unlike normal extinction mapping, we're actually going to get some kinematic information on the ISM. So this is going to be really exciting. I think some exciting stuff is going to come out in the next few years. Then nice review talk on H1 mapping by Juan Solar. This is just showing one of the maps. Again, remember warning kinematic distances. Okay, so you can't get reliable distances inside the solar circle and in an anti-center direction. But the H1 gas really maps really well the warp, and as you go to larger distances, you see that the warp is not a nice symmetrical feature, as we see in the stars. In the inner parts, it's symmetrical, but then it becomes kind of wobbly, even more distorted. The other cool thing that he was showing us was that the resolution of some of the surveys that are being done now are really high, and they're able to see this filamentary structure and map the filamentary structure in different velocity bands, so different distances, and sort of investigate how these filaments, how their orientation changes in different parts of the galaxy. And this is a map in red and blue is where he's essentially, the red shows where the filaments are parallel with the galactic plane, and blue is where the filaments are vertical to the galactic plane. And he's overplotted here in green H2 regions. And you see that where you have lots of H2 regions, the filaments are vertical, which is sort of this galactic fountain idea. And you have the H2 regions are blowing stuff out of the disk, and you have flows that go vertical to the galactic plane, and you have this stuff happening. So that's really kind of cool. And this was exactly what this workshop was for, right? Bringing different data sets together and comparing to make these kind of discoveries. Very cool stuff. So going to H2 regions, I just mentioned them. So H2 regions in galactic structure have a very famous and infamous reputation, because it all started, I think the first picture that people really got behind in terms of our galaxy. Yeah, our galaxy has 4 arms. See, you can see it from the H2 regions. And this was a map that was done by George and George in 1976. Again, I should add here warning kinematic distances. Only for the H2 regions close to the sun do you have photometric distances. All this other stuff out here are kinematic. And also, they're very judiciously did not show you any error bars on the spot. Okay, it's not so clear really how many arms we have looking at the H2. This was in 1976 now. So this is what the data actually looks at. For H2 regions, again, we only have a position and a velocity. So this vertically, I'm showing this is galactic longitude and velocity. I'm used to seeing it turn 90 degrees, but Trey Wenger, who gave the presentation on the H2 regions was showing this. So what's cool though is that there's all these new discoveries. You can see H2 regions all the way to the other side of the galaxy using radio and near infrared data. And so there's a bunch of these that still yet to get their, he's working on getting, driving kinematic distances, but he's also makes a very strong point in his presentation, which I really like, is that this is the data. And also he pointed, kinematic distances got dissed a lot during that week at Lorentz Center. And one of the slides he's pointing out is that if you actually do sort of some analysis on what the uncertainties are, they're like a kiloparsec. Yeah, so the kinematic distances have really a huge uncertainty. So he's saying what we should be doing is modeling the data, right? Rather than driving kinematic distances and trying to plot things in XY on the XY plane, let's see what spiral arm model actually reproduces the data. And he's working on a program to do that. So work in progress, but I absolutely agree with his approach. I'm not so confident you will not still have ambiguities, perhaps. But still, I think it's the right way to go. So the last word here before I end is on masers. Katharina Emer, who's worked with Mark Reed on masers. Again, it's this problem again. This is the masers that have measured parallaxes. The nice thing about this data is that the precision is very high, relatively speaking. The circles here, the size of the circles are with respect to uncertainties. But really uncertainties is in the direction of the line of sight. So in the first and second quadrant, we have lots of data. And here we have, very little data. Not because there's no masers there, but just because we haven't yet had time to have their parallaxes derived. Also, there's a north-south problem. There's only one unit to do this kind of precision. You need a VLBI, and there's only one VLBI in the southern hemisphere, and that's in Australia. So that's an ongoing program, but one of the things I want to point out though is that she in this presentation, she focused in on this area, this inner region. And what's really nice is you can see these where these masers are. This underlying figure here is a simulation gas flow, and you can see that you have actually lineup features, but even more impressive is if you do the velocities. So on this side, this is the model velocities. And you can see actually the data that you really can model very, very well, this interface between the bar and the spiral arms. Yeah, and that's kind of pretty exciting how they can, because you have to really tweak the model. You have to get the bar at the right angle at the right velocity to get something that lines up, but that means that the data is really constraining the models. But the future does look bright. This is an all-sky survey of masers where we know where they are. This is the north, so many of these have parallaxes, and this is the south. We're still waiting for parallaxes, but in the future they will arrive. Let me also say that this assignment, she showed the assignment according to spiral arms, but I would prefer to show this data without that, because I don't think it's really terribly clear. I mean, the masers are great because their precision is really good, but it's sparse data. Yeah. And I think also maybe the galaxy is not as neat as we would like it to be. That was one of the things that came out of the conference. Bob Benjamin gave a really nice history talk at our social dinner and showed this slide, which kind of is really interesting. This is only up to 1993, all the different spiral arm models that had been proposed in the literature for the Milky Way. And only one of these would become very popular after 1993, and it's this one right here. It's Taylor and Quartz. And the reason why that became popular, it wasn't because it was better than all the others, because they made available the code so you can actually plot, right? I mean, I remember when I was mapping Kobe data, right? I need a spiral arm model, and there it was, right? Already coded up, I could just plug it in, make it work. And that's why it took over. Because they made their source code available. So, at the very last day, we had this nice discussion on, we put up this figure and we asked people in the audience, the participants, what do you not like about this picture? This is the most popular portrait of our Milky Way you'll find. People use this all the time, the hurt image. And there was a lot of, I only list some of the complaints about why this is wrong. I agree with all these. In particular, I think that our galaxy is not so symmetric and clean and perfect. Yes, it does have a bar. Yes, we have a good idea what the angle is with respect to the sun's position. But I think our galaxy probably is much messier in the outer parts, especially. And figuring out, and we only see, we're only seeing a piece of with Gaia, and it's hard, until we see more and get better data, we're not going to be able to make a picture, like that, where we can say that's the portrait of the Milky Way. But we're getting there. So I don't think we didn't reach a consensus of how many arms. We didn't even debate it. I think I used to believe the Milky Way had 4 arms. I think if people ask me how many arms it has, I would say I don't know. I don't know how many arms it has, but I'm pretty willing that it's going to be kind of messy. And thank you very much.
For new questions?
Maybe online, someone.
No, I will check it now. But I have a question. Very nice talk, thank you. Okay, it's general, but I'm really curious. With DIR4, what you have on this DIR4, with all this data, which improvement do you expect? I know it's impossible to predict.
I think in the astrophysical parameters, we're going to have a huge improvement.
Astrophysical parameters. So
Yeah.
you point on
And this really allows you to pull out, different kinds of stars and select. So you'll have cleaner samples, and we'll be able to go fainter. So I think the mapping that we saw with the giants that I showed will extend even further. And in some of the systematic effects in that map, you have to model that data. You have to take into account the distance errors are affecting you systematically in different directions. So this will definitely help as well. More Cepheids. I think we already know most of the Cepheids. The numbers might increase a little bit. Fainter maybe. The problem is to identifying a Cepheid, you need the optical. Once you know it's a Cepheid, then you can go to the near infrared and do distances. But in the near infrared, a Cepheid is not clear. It's not so clear it's a Cepheid. I think in identify you have to. Yeah, but the amplitudes are much smaller and much more symmetric. So you don't have this classic sawtooth profile that you see now that helps you identify it. So but of course, better proper motions, better kinematics.
Everything will be better.
Yeah.
So given the new information on kinematics that we have, what do you think is the more likely spiral arm model, the